We are the Dark Energy Explorers with HETDEX. My name is Audrey Hopkin.
I'm Charlotte Myers.
Diya Kumar.
And I'm Madison Brown.
Before we dive into the research, let's cover some background information. What is dark energy? The short answer is no one knows, but we're almost certain it exists. Much like dark matter, we can't detect it directly, but rather can only observe its influence. As more research reveals its significant impact on the expansion and evolution of the universe, more and more astronomers are seeking to unravel the mysteries of dark energy. The first evidence for the existence of dark energy arose in 1998, when two independent teams of astronomers made the same surprising discovery. Both teams were studying Type 1a supernovae, which brighten and fade in predictable cycles that allow astronomers to reliably determine their distance. When comparing this value to the distance calculated using their redshifts, they could infer the universe's rate of expansion. We've known that the universe is expanding since 1929, when Edwin Hubble published a paper detailing the correlation between a galaxy's velocity and its distance from us, shown in this graph on the right. However, how this rate of expansion changes tells us about the ultimate fate of the universe, and this is what teams of astronomers are trying to determine. In the supernovae study, it was found that these stars were farther away than expected, meaning they did not fit Hubble's model. In other words, the old model not containing dark energy does not fit the data at higher and higher redshifts. They came to the conclusion that the expansion of the universe is accelerating. The invisible force that causes the expansion to speed up was named dark energy. Though we don't know exactly what it is, we can clearly see its effects on the nature of the universe.
So what does this mean for science? Dark energy completely changed the way cosmologists understood the future of our universe. After Hubble's discovery, the prevailing theories were that the universe's expansion would either reverse or slow down and come infinitely close to stopping. If there was enough matter in the universe, gravity would be the dominating force. Eventually, the universe would shrink back into a singularity and possibly start expanding again in an infinite cycle. This was called the Big Crunch or Big Bounce scenario. If there wasn't enough matter to cross that threshold, however, they thought eventually the expansion would slow down until it became imperceptibly low. And eventually all the stars would burn out, all the galaxies would dissolve, and all the black holes would evaporate. This was known as heat death or the Big Chill scenario. These scenarios become very unlikely once we take dark energy into account. Since the expansion of the universe is speeding up, it's more likely that galaxy clusters will move farther and farther apart, faster and faster, until they get to a point where the light emitted by them will never reach other galaxies. This sounds impossible, but the universe can actually expand faster than the speed of light. While matter itself can't move through space faster than that, space can stretch at such a rate. So eventually there will be a time when we won't be able to see other galaxies. Eventually these will dissolve and space will expand between individual atoms so fast that they'll never interact with anything else ever again. Our project is to aid in citizen science for the Hobby-Eberle Dark Energy Experiment, or HETDEX. HETDEX's goal is to create the largest map of the universe yet by measuring around 1 million galaxies 9 to 11 billion light-years away, or with a redshift value of 2 to 3. This map will help astronomers understand the influence of dark energy on the universe's expansion throughout time. This map will be made of 150 spectrographs called the Visible Integral Field Replicable Unit Spectrographs. These spectrographs gather light from galaxies and split them into their spectra, which can reveal the galaxy's chemical composition, its redshift, and the speed it's moving away from us. Astronomers then convert the object's redshift, or its motion away from us, into distance, and they can then produce maps of our universe.
The next step astronomers take to determine the influence of dark energy is through using a concept best explained by studying baryonic acoustic oscillations, or sound waves, from the first 400,000 years of the universe. In the early years of the universe, it was very dense, compact, and a liquid-like mixture of matter and energy. Sound waves created by disturbances rippled across this dense universe, and at about 400,000 years, the universe became cool and thin enough for the ripples to cement into a specific size. Telescopes have measured the crest of these ripples in the universe, and that forms a basic measurement. As the universe expands, this basic measurement is kept, though it does grow as the universe grows. HETDEX uses this concept of a basic measurement by measuring the distances between distant galaxies at different times in the early universe. The maps created with the galaxy's redshifts are incredibly important here, as the astronomers want to measure distances between galaxies that are within the same time period, or have a similar redshift. By observing how the distance between galaxies has changed with respect to time, we are subsequently observing the influence of dark energy with respect to time, or its influence at different epochs in the universe's history.
Our task was to sort between nearby and distant galaxies. We filtered out images that were just noise, nearby galaxies, or stars, so that the data wouldn't be contaminated by non-distant galaxies. Our work, as well as the work of other citizen scientists, helps astronomers to develop confidence in their classifications of distant galaxies. They will then be able to create a detailed map that will be used to calculate the change in the expansion rate of the universe over time, revealing the role of dark energy at different eras of the universe.
This is how we collected the data for our project. We were given images like the one you see on the left. It has 3 components. First, we could determine if what we were looking at was an actual object or if it was just noise or static. The 5 panels on the left and the spike at the bottom help us determine that. If no black dot appeared in any of the panels, or if the data points didn't correspond well with the line, then we classified it as noise. If there was a black dot and the data corresponded well, it was an actual object. Then we'd look at the top right image to determine whether the object we were looking at was a nearby galaxy or star, or if it was actually a distant galaxy. If the black region was larger than a certain threshold indicated by those small colored circles, then we classified it as nearby. If it was smaller than the circles, we classified it as distant.
As previously shown, galaxies are classified primarily based upon the relative size of the dark circle in comparison to the colored circles. These colored circles are given by the research team on Judit.org. On the very left, the dark circle is larger than the colored circles. Therefore, it is classified as a nearby galaxy. The middle image shows the opposite of this. The dark circles are smaller than the colored circles. Therefore, this is classified as a distant galaxy. On the right image, there is not an exact dark circle to be used for comparison, nor does a spectral line graph demonstrate a real source as mentioned within the last slide. As seen on the pie chart on the right, you can observe the actual data distribution of galaxy classifications in the given catalog. 42.8% of the given catalog were distant galaxies, 47.2% were nearby galaxies, 7.9% were found to be noise, and 4.4% of the data samples were difficult to identify. The 4.4% of data samples that were difficult to identify provides an estimate of the error for all groups. Additionally, observational bias had the potential to influence error and data observation. We're closer to the nearby galaxies. Since these stars and galaxies are bright, this may appear more frequently within our data catalog. Essentially, HEDTEX aims to identify galaxies of interest, that being distant galaxies 10 to 11 billion years ago are light and alpha emitters.
This reveals that a lot of the data in the catalog right now is misleading and needs to be filtered out, as a large majority of them are not in the desired redshift range. Over half of the data is comprised of nearby galaxies, stars, and noise, when the scientists only want to look at distant galaxies. This also tells us that more people need to get involved for the project to succeed. It's a fairly new project, which requires a lot of confidence in the data being used. A lot of the data we are asked to sort through can be ambiguous, with it being hard to identify distant galaxies from noise, and sometimes even nearby galaxies or stars with distant ones. Involving more people will eliminate any error that an individual citizen scientist makes and result in a more successful project.
Additionally, computers are not as accurate as human visual classification. They often pick up too much noise from surrounding celestial bodies. Visual classification allows for the development of AI computer algorithms to classify nearby or distant galaxies. Understanding the approximate error and difficulty in human classification will provide a basis for computer algorithms, thus expanding the understanding of the error on future computer algorithm galaxy classification systems for HEDTEX. This, in turn, provides a rationale for citizen science for this project.
The CEASE program allowed us to explore methods of contributing to astronomy research as high school students. By utilizing citizen science projects, we were able to contribute to astronomical research in an environment that was suitable for our ability and instrument accessibility, while also challenging and encouraging our background knowledge. The challenge, of course, was the virtual environment, which added a barrier to communication and the type of work we were able to perform, though we still did get a lot out of this experience. This opportunity was invaluable to us, and we're extremely grateful to have been able to participate.
We'd also like to acknowledge and say a big thank you to all of the CEASE mentors, organizers, and presenters.